Hello and welcome to the channel of Sigma Plus Industrial Solution. In that video, we're going to discuss about the calculation of the sigma level. And in recent videos, we have discussed the calculation of the sigma quality level for a discrete data type, such as counting the defects in a certain process. But what if the data that you are dealing with is a continuous data type? How can you calculate the sigma quality level? I should consider that before watching that video that you have the basic knowledge and understanding about the histogram, the standard deviation, and the calculation of the process capability. And if not, then I would recommend that you have a look to our old videos where we are explaining those terminologies. Okay, so in fact, as a quick refresh for the sigma quality level, the sigma quality level, in fact, is a statistical measure, and it's measuring our design processes capability to achieve certain targets, business targets, quality targets corresponding to a certain specification limits. Okay, so the Six Sigma level is also measuring the quality yield. So the higher as the quality, then indeed the Sigma quality level should be high. So it's all about the process capability. And as a quick review on the definition of the process capability, which is measuring how well is the performance corresponding to the specification limit. And it has a look on two different factors, two important factors. The first factor is the mean or the location of the sample mean corresponding to the specification limits. And the second factor is the spread of the data. And of course, the less spread of the data is the best choice, and especially when it is centered between the specification limit. So if we have a look on the three different scenarios of process capability, we will see that in the first scenario, we have a high range of data distribution that it's exceeding these customer specifications limit or the quality specification limit. And as such a scenario, we describe its process capability as weak. And there is a high probability that your processes or your process will not be capable to achieve the targets as per the quality targets. And the second scenario, we can see that the data distribution curve of the process capability is dropping all inside the specification limits. And we describe such data distribution as a roughly capable process. Why? Yes, it's all dropping inside the specification limit, but this doesn't mean that you will have a long sustainability of a strong, capable process to achieve the targets. It means that after a certain period of time, you might see that there had been some kind of shifts for the data distribution that caused the process to be not anymore capable to achieve the target. So you might have some shifts like that, and you can see that it will exceed the specification limit, and the process will not be anymore capable to achieve the targets. But in fact, the third scenario is known to be the best one. Why? Because as you can see, the data distribution is more narrow and centered in between these specification limits, which is helping to have a better process capability. Okay, now to better understand what we have discussed, let's take an example. The example says that a service team in a juice factory had just finished the service work for the main injection machine, but one of the production workers is claiming that the machine is not properly working, as the juice volume injected in the plastic bottles are less than the lower control limit. The volumetric tolerance of the juice in each bottle should be between the 455 and the 475 milliliters. So you can see we have already the quality specification limit, which is that we have a lower specification limit and the upper specification limit. It was decided to test the machine for 2 weeks before taking a decision to stop the production and reconduct the surface works. In certain circumstances, it's not easy to take a decision to stop a high mass production and to perform a service work. So that's why it's very good that you support your decisions with some data facts. A random samples of 5 bottles will be taken on daily basis for the sake of calculating the short and the long-term process capability. So considering that the process standard deviation is 2.3, okay, so it's important also to understand the standard deviations of the process, and I will explain the role of the standard deviation here, how it will affect on the process capability and the sigma level. So calculate the process capability index and the sigma quality level of the injection machine. So as you can see, this is the tabulated form of the samples. So in the first day, we gathered 5 bottles, and the average volume of the 5 bottles was 457.27 milliliters. And we have repeated the same for the rest of the days, where we collect the average volumes for each sample on a daily basis. So as you can see, we have a sample size of 14 bottles. Okay, I understand that some of you can come back to me and say, oh, but the sample size is very low, and there will be a high percentage of error. Yes, you are right, but please do understand that the goal of that example is that we want to explain how to measure the process capability and the sigma quality level. And I do agree, but in the real life, that the sample size should be much larger than that. And we have other specific formula to calculate the sample size for the sake of reducing the errors that could be resulted from the sample size. So the first thing that we can describe that sample size, we can do some kind of statistical description, where we can see that the mean of the sample size is 454 milliliters, and we have a range of 7.33 milliliters, which is the difference between the minimum and the maximum volume that we got resulted from the sample size. Okay, and the next information that we can get is the target mean. So we have the lower specification limit is 455 milliliter. The upper specification is 475. So the target mean will be the middle value between the both specification limit, which is the 465 milliliters. Okay, and we can also start to plot the histogram of the sample size that we have. And after plotting the histogram, we can plot the specification limit with the target means. Now, if we look to the shape of the data distribution, we can see that we have almost a normal distribution, and that's very important to know, because as a golden rule, if your data distribution is not forming a normal distribution, please do not follow those rules to calculate the process capability and the sigma level, because that will be dropping in the basket of the non-parametric statistics, where we have to convert the non-normal distribution to a normal distribution. And then at that case, you can implement the following formula. Okay. Now, also another important role is to know that as the standards, that the number of standard deviations between the specification limits are always 12 standard deviation, right? So we have 6 standard deviations after the target mean and -6 standard deviations before the target mean. Okay, so if I know that the distance between the lower specification limit and the upper specification limit is about the 20 milliliters, because 475 minus the 455 equal 20. And I want to distribute those 20 milliliters in 12 sections, which are the 12 standard deviation. So I can say that the specification standard deviation will be about the 1.6 milliliters, right? So the 1.6 milliliters is representing the process standard deviation, and we can utilize this information to compare it with the standard deviation of the process, right? So this is, if I look to that distance here, that's the standard deviation that by which we calculated, the 20 milliliters divided by the 12 standard deviation, which will be equal to 1.6. So it's not 1.2. So that is known to be the specification standard deviation. So the first thing that I can have a look on it is the comparison between the process standard deviation, okay, and the specification standard deviation. This can give me the process standard deviations if, as per the example, was 2.3. So we can see that the standard deviation here is a little bit higher than the specification standard deviation. But we cannot say now if the potential capability is strong or weak. Okay. First thing that we use to calculate, or or before that we go to the calculation, I just want to highlight that the process capability is representing the ratio between the voice of the process and the voice of the quality or the customer. So as much narrow is the voice of the process corresponding to the voice of the quality, that will be an indication that you have a strong or capable process. Okay, the first thing that we usually do in the calculation is to calculate the potential process capability, which is known to be the CP. And the CP here is looking to 2 points. The first one is the distance between the upper specification limit and the lower specification limit. And the second one is the standard deviation of the process. Okay, so as you can see, it's just looking to the ratio between the voice of the customer and the voice of the process. And this is known to be the potential process capability. Okay, what do we mean with the potential process capability? Is the opportunity of an improvement. It is not the instantaneous process capability. It's not the real process capability, but it is the opportunity of the improvement that can be done. So as we can see that the CP will be equal to the upper specification limit minus the lower specification limit, which is the 475 minus the 455, which is equal to 20, and divided by 6 multiplied with the standard deviations, where the standard deviation is 2.3. So 20 divided by 13.98, we get a potential process capability of 1.43. And refreshing again the rules of the process capability, if the process capability is higher than 1.3, then we usually describe the process that it is a strong, capable process. But remember that in this case, the process capability, it is the potential process capability, which means that we have a strong opportunity to improve the situation, which in other way, we can say that there is a remarkable assignable cause for the shift of the sample means corresponding to the target mean. Now, the main issue that we can get now, and from the first look to the graph of the histogram and the specification limit, is the big shift between the mean of the data distribution, which was 454, and the target mean. This is our concern. And what is the target that we need to do is to shift to the right side, to shift the data distribution to the right side. So we try to keep it in the center in between the specification limit. Okay, so we've been discussing about the potential process capability. But what about the real process capability, which is describing the instantaneous capability of the process or the current process? So, as all of us, we know that the process capability index, the CPK, is calculated by finding the minimum value between the CPKL, which is the process capability corresponding to the lower limit, and the CPKU, which is the process capability corresponding to the upper specification limit. And we can see that the CPKL is the X, which is the sample mean, or X bar actually, minus the lower specification limit divided by 3 multiplied with the standard deviations of the sample. Okay, so we have 454.7, which is the sample mean, okay, minus 455 milliliters, which is the lower specification limit. Okay, and so the result of the equation is 0.3 divided by 6.99. So the CPKL is 0.042. And we do the same for the CPKU, the process capability corresponding to the upper specification limit. And the result is 2.9. So the minimum value is 0.042. So we can say that the process capability index is 0.042. So indeed, this is a very, very weak process capability, and we cannot continue running the process with such value. Okay, but taking in consideration again that you have a very strong opportunity of improvement, which means that there is a very clear, a very remarkable assignable cause that is leading to that poor performance. Okay, now we have understood how to calculate the process capability, but how can we conclude the sigma quality level from the process capability? Now, if we refer to the tabulated forms for the process capabilities and the yield and the sigma quality level. Okay, now let's see first the sigma quality level corresponding to the potential process capability. So our potential process capability was 1.43. So if I refer to the 1.43 from the tabulated form, and by the way, this kind of table, you might Google it and just write in the search table of process capability and sigma quality level, you will find thousands of tables that you can, from where you can utilize it to get and conclude the sigma quality level. Okay, so by looking to the process capability 1.43, which is the potential, again, yes, I know here it's CPK, it's the real process capability, but we are looking what could be the potential process capability, the sigma value for the potential process capability. So you have two sigma level. One is called the short-term sigma quality level, and the second one is known to be the long-term. And the short-term is the 4.3 sigma level. Okay, and the 4.3 is equivalent to 99.7 quality yield. What does it mean? It means that when you have a quality yield of 99.7, that the probability of defect for each batch of juice bottles that will go in to the injection machine, the probability of defects is 0.3% only, which is a very good quality yield and a very low probability of defect occurrence. Okay, but this is known to be the instantaneous or the current process capability on sigma quality level. But in the long term, it's 2.8. So from where did it come, the 2.8? Well, there is a standard rule that say that by time there is always a shift in this of 1.5 standard deviation. Okay, so that's why you can see that if you subtract 1.5 from each of the short-term process sigma quality level, it will give you the long-term process sigma quality level, which means that after a while, do not consider that you will have the same sigma level that you have calculated. No, there is always shifting for the data distributions. So that's why we take as a statistical rule that for the long term, we consider a 1.5 standard deviations shifting. So that's why if you see now 4.3 minus 1.5, it is equal to 2.8 as a long-term sigma quality level. Okay, so we can see that, okay, based on the potential improvement that we can achieve, we will have a 4.3 short-term sigma quality level and a 2.8 long-term sigma quality level with a quality yield as 99.7%. And again, as we highlight, this is for the potential improvement that can be done. But what about the sigma quality level for the current scenario, which indeed, as you can see, it will show us that we have a very weak quality yield. So our CPK was 0.042, and the 0.042 CPK, it's dropping somehow between the 0.07 and the 0.03, which means that our sigma level will be dropping somewhere between the 0.1 and the 0.2. So by simple calculations, we can see that the sigma quality level, the short-term sigma quality level is 0.13, while at the long-term sigma quality level, if we subtract the 1.5 standard deviations, we will have a minus 1.37. Of course, there is nothing called minus 1.37 sigma quality level, but we can say it's a 0. But if I look to the sigma level of 0.13, which is equivalent to a quality yield of 83%, what does it mean? It means that, imagine that each batch of the juice bottles that will go inside the injection machines, there will be a probability of defect of more than 92 or 91% of the bottles will be not accepted and rejected. Okay, so indeed, such situations, there is a must that we need to stop the machines and call for the service. At the end of that video, I thank you for your good listening and watching, and see you for the next time. Thank you.